All right, good morning, everyone. So let's see. Today we are going to talk about solving quadratic equations by factoring the square root property and also the quadratic formula. So, any questions from last time? I actually don't really have anything remaining from the last section that I wanted to specifically go over. So, unless you guys have specific questions that maybe were confusing you, or if you guys really do want to see some more examples, I think we're okay to move on. What do you guys think? You guys can chat or react or just unmute as well. Okay. All right, so let's see here. So we're going to talk about quadratic equations, and quadratic equations are where solving equations get a little bit more complicated. So a quadratic equation can get a little bit more complicated in regards that this right here is what we consider a quadratic equation. Written in standard form. And you're going to be using this standard form a lot because it's how we start solving quadratic equations in their most basic way. So if you remember, just like when we had ax plus by equals c when we had linear equations, this is the quadratic equation equivalent. And the big difference between linear equations versus quadratic equations are we now have the second power of x. So the process of solving it is much more complicated because now it's not just a matter of isolating x, because if I were to say, oh, let's try and isolate x and solve for x in this case, what I could do is subtract the c over and then factor an x out here. But if you notice now, the way that I would start factoring the x out leaves an x remaining inside. So now I can't divide by this factor out in front and then say, oh, x is equal to that, because x will appear in both sides of the equation still. So I haven't said x alone is something over here. So now I can't solve it the normal way. So quadratic equations are harder. And now what we're going to do is talk about how to solve them by factoring. So we'll just start off with an example. So if I were to give you this equation right here, what I want to do is write this as, and we've really been doing this a lot already. And this is some type of content that the curriculum still assumes you know to some extent. So I don't have to start from the baseline. But if you guys are still confused on my thought process on how to factor these, please let me know. But what I want to do is write this as a product of two linear terms. Because if you notice, if I were to multiply these linear terms together, I would get these x squared terms out when I multiplied the first terms together. So it's a good baseline process, and we're going to be doing the same thing. So what we're going to do is think of two numbers who, when are multiplied, are equal to -6, but when added together are equal to 1. That's the one coefficient on in there. So you can think of a few factors of 6. There's 1 and 6. There's 2 and 3. There's 3 and 2, which are the same thing. So we've exhausted all of the factors. And if you notice right here, if I play with some signs of 2 and 3, I will get them to sum to 1. It's going to be -2, +3. And if you notice, this is equated to 0, which is very important because there's a property that says if what is this property called? I think it's called the zero factor property. And it's the base idea of how we solve quadratic equations by factoring. If a times b is equal to 0, a is equal to 0, or b is equal to 0. So what this factored quadratic equation tells me is, since this is equal to 0, and say I called this a and this b, then a is equal to 0, or b is equal to 0. And this is what provides us the solutions to the quadratic equation. This means x is 2 or x is -3. And if you get really good at this, you can almost pick it out from the way this equation is written. I have the product of these two terms. So if any of these two terms are 0, this would be a true statement. So if x was equal to 2, this term right here would be 0, and this would be a true statement. If x was equal to -3, this would be equal to 0. So it's multiplied by 0. So it's equal to 0. So it's a true statement. But this would be the written out form of how you would solve it beyond that. So let's try some more. So how should I go about solving this equation now? I've changed the way it's been written just a bit. So now we have this slight alteration to the question. So we need to learn how to adapt to it. Notice this equation is not equal to 0 right now, like the one we had above. We had this equation right here, and it was equal to 0. So we had the A term, the B term, and the C term. And we were able to factor it pretty straightforward. But now it's not equal to 0, but we can very easily make it equal to 0 by subtracting that 6 over and just leaving 0 on the right-hand side. So this is a note for you guys. In order to factor quadratics, the quadratic equation must be in standard form. I.e., ax squared plus bx plus c equals to 0. So the a's and the b's and the c's, it doesn't matter that much so long as it's equated to 0, because what we want to use is the zero factor property, and the zero factor property requires it be equated to 0. Because when we break this sum of or difference of terms up into a product of two different terms, then we can say, oh, the one of the factors of the product is 0, or one of the other factors of the product is 0, and that's a true statement. But if I were to leave it like this, so let's say we don't know, we have to leave it in the standard form, and we just go about, oh, maybe I can factor this x out. And now what you've done is you've set up a harder question for yourself. What you're looking at is, where is a number x minus 5 times x equal to 6? And this is a much harder statement, because maybe there are multiple factors of this that work. So maybe this one isn't a great example to actually plug in some values, but this will give you many different solutions, and it will make the question actually much harder, because now you're looking for random combinations of numbers that, if I were to pick like 7 and then 6 or something like that, maybe that works out to be equal to 6 like here. But now we don't have the clean zero factor property in order to give us the solutions. So this is wrong. I can't think of an example specifically where I can illustrate how multiple combinations of numbers work, but there are out there, and they are the examples for why this type of solving of quadratic equations is wrong. You need to equate it equal to 0. But once you equate it to 0, the process is actually pretty straightforward. Again, I'm going to say this is a product, two different terms. And all I need to figure out is what these numbers are in here. And my rule is, I need two numbers that when multiplied are equal to -6, but when are added together are -5. So some factors of 6, 1 and 6, 2 and 3, and we're basically exhausted with our factors. And if you notice, I guess 2 or 3 or 1 or 6 can work out for us. So we need to think about this a little bit. So in order to get 2 and 3 to add to some form of 5, they need to have the same sign, right? They either have to be 2 and 3 positive, or -2 and -3, adding together to get -5. But if I multiply -2 and -3, I get +6. So any form of 2 and 3 actually can't work out for us. So it has to be some version of 1 and 6. So let's do -6 and +1. Adding them together, I don't want to say equal to here. Adding them together, I get -5. Multiplying them together, I get -6. So it's going to be +1 and -6. So then my next line is using the zero factor property. X plus 1 is equal to 0, or x minus 6 is equal to 0. And we'll get faster and faster at not having to write this out. This line that I'm currently writing, we'll just be able to pick out the answers right away. But this means x is either -1 or +6. Well, it will have two solutions. So every quadratic will have at most two solutions. So the way a quadratic equation looks is it's a parabola, meaning it has this curvature to it. And if you look right here, if I set this equation equal to 0, what I'm really doing is setting y equal to 0. And I'm finding these x-intercepts. These right here are x-intercepts in reality. and we'll have two solutions. Okay, let's try another example. So first, ask yourself, am I in standard form? If I want to factor this quadratic equation, I must be in standard form. So am I in standard form?
Yes.
Yes, we are in standard form because the equation is equal to 0. So now I can think about the factors. So let's look at 15 right here because he's the pivot that we're looking at. 15 has a lot of factors. 1 and 15. 3 and 5. Oh, I guess it doesn't have a lot of factors. I don't know what I'm saying. So it looks like combinations of 3 and 5 can probably get us to 8 rather than 1 and 15. So we'll do 3 and 5. And if you look, 3 times 5 is equal to 15, just as we wanted. And 3 plus 5 is equal to 8. So it's positive 3 and positive 5. So let's see if we can take a leap now. Can you guys pick out what the solutions for this quadratic equation are without doing that extra line of algebra that we have been doing? What are the solutions?
-3, -5.
Yep, -3, -5. Because just by looking at it, if I put -3 in here, this quantity would be 0, meaning 0 times anything else, doesn't matter what that is equal to 0, and that's true. Same with -5. If I put -5 in this term right here, I'll have 0 times something else, and that will be 0, which is going to be true. So these are our two solutions. Let's try another. Let's see. I won't make it that hard. So am I written in standard form? Yes. So we can go straight to factoring. (21). Let's look at some factors of 21. There's 1 in 21. 21 can't go, or 2 can't go into 21, so we'll skip to 3. And there's 7. And that's going to be it. So there's no plus or minus combination of 1 and 21 that can get me to -4. But 3 and 7, I certainly can. So adding -7 and +3, I get to -4, so that's fine. +3 times -7 is -21, and that's also fine. So our solutions are -3 and +7. Okay, so these were all examples of factoring. Of factoring. Factoring being the technique we use to solve these equations. But it's not always easy, and it's not always applicable. Sometimes we need to use other techniques. So when a is equal to 1, a being that term that's way outside in front of adjacent to the x squared term, that a term. Notice a is 1 here, a is 1 here, a is 1 here. When a is 1, it's relatively easy. But there are examples when a is not 1. So I'm going to leave this as just a little blurb right here. But when a is not equal to 1, meaning -2, +3, +18, anything, it's harder. So let's try some examples. We are still going to use some technique of factoring, but it's going to be a little trickier. So I'll call this section when a not equal to 1, how do we factor? Because quadratic equations can vary a lot, I'm trying to compartmentalize the techniques for you guys to use, because once you've compartmentalized some techniques, then you can break down every question into which compartment should this be in to solve for it, and it will make these questions much easier for you. So we'll start off with an example. So right away, if I were to naively guess and say, oh, okay, I'm going to factor this like normal. It's in standard form. I'm going to think of those numbers, but let's just look at these two things right here. Notice if I were to redistribute these factors together and make it back into a quadratic, x squared times x squared will not be 4x squared. So the simplification doesn't work this way. What we need to do is have something like 2 and 2 here, or 4 on one of them, and x on the other, something like that. Because then when I multiply 2x by 2x, I will get 4x squared out, or 4x by x, I will get 4x squared out. And you'll see how that actually does happen when we solve this a certain way. So here's the trick. What I'm going to do is look at what is a times c. So what is a and c? If I were to write this quadratic equation in standard form, it is in standard form, I can just pick out what a and c are. So what are a and c in this quadratic equation?
4 and 9.
Yep, 4 and 9. So I'm going to look at 4 times 9. That's going to be 36. And now I'm going to look at b. B is equal to 15. So what I'm going to do now is think of, let me put this over here. I'm going to think of some factors of 36. There's 1 and 36. There's 2 and 18. There's 3 and 12. There's 4 and 9. There's 6 and 6. And I think that's it. What I want to do is look at the factors that will add together. Maybe I flip a sign or something like that to get positive 15. So adding 1 and 36 probably can't get to any form of 15. 2 and 18, there's no form of, changing the signs to get to 15. But 3 and 12 directly add to positive 15. So here's our winner. And now what we're going to do is I'm going to break up this middle term as two separate terms. Do it over like this. So This equation has not changed. All I've done was separated 15x's into 12x's plus 3x's. And we know to split it up into 12x's and 3x's from these factors right here. This was the point of this extra work. But now what I'm going to do is factor each piece individually. I'm going to factor this guy and this guy. So what are some common terms I can factor out of 4x squared and 12x? Well, certainly I can factor an x out, but I can also factor a 4 out. If I factor a 4x out, I'll leave an x plus a 3. Plus, and I'm going to factor a 3 out of the other term. And these, when you've done it correctly, these will and must match in order for this technique to work. If you do the technique and these terms do not match, you have done something wrong. But now, what I can do is, since these match together, I can factor them out of both terms. So what I did is I took this quantity and pulled it out of 3. I took this quantity and pulled it out of 4x. So what I really have is this quantity times these two different terms. And if you were to take this and redistribute it to the 4x and the 3, you would get back this equation. So it is a valid factorization. But now we've achieved what I promised, which was we have a 4x plus something times an x plus something. So we factored this correctly. So this means either x plus 3 is 0, or 4x plus 3 is equal to 0. And this is where maybe still doing the algebra is useful for you, because we need to do this extra algebra. This term here is okay. We can still see that if I plug in -3, I will get 0. So x certainly is -3. But it's harder to see what would make this term 0. Certainly there is a solution for what will make 4x plus 3 equal to 0. But maybe we need to do that algebra out. So x equals -3/4 and x equals -3 are the two solutions to this quadratic. So this is called factoring by grouping. It's tedious and will take some practice, but it's not bad once you've gotten that practice in, because it'll just be an algorithm in your mind, right? You're going to multiply a and c together. Then you're going to look at factors of a times c and see what factors make the b term. Once you've got the b term, you split up the b term into those two factors you found, and you factor it out, and then you can do the same thing as before. So we're going to try another example. All right. So someone guide me through it. What is the first step I should do?
Multiply 12 and 2.
Say that again.
Multiply 12 and 2.
Yep. So we need to find a times c, which is 12 and 2, which is 24. So now I'm going to find factors of 24 that make 11 in some way. Maybe I change a sign or something like that. Let's look at that. So factors of 24. There's 1 and 24. There's 2 and 12. There's 3 and 8. There is 4 and 6. And I think that's it. So which set of factors do you guys think is the best candidate? 4, 6, 3, 8, 2, 12, 1, and 24.
3 and 8.
3 and 8.
Yep, 3 and 8, because when I add 3 and 8 together, I get 11, which is the thing that I want. B is 11. So B is the same thing as 3 plus 8. So those are our winner categories. So I'm going to rewrite 11x as 3x plus 11x.
Isn't it supposed to be 3 plus 8?
Yeah, I was looking at that and I'm like, something was wrong. Thank you. So what I'm going to do is group this. This is why it's called factor by grouping. I break these guys up into 2 different pieces. And what I'm going to do is factor out a 3x in this term. So I'm going to leave a 4x plus 1. And then now over here, I'm going to factor out a 2 to get 4x plus 1. As the prophecy foretold, these terms match, and they must match for this concept to work. Because now what I'm going to do is factor out that 4x plus 1 to get the quantity 3x plus 2 times 4x plus 1, which is equal to 0. So this was a very complicated one. And what we need to do now is do the algebra involved in both of these, because it's going to be harder to see. I can't just pick out what the solution is. So 3x plus 2 is equal to 0, or 4x plus 1 is equal to 0. Doing some rather quick algebra. We get the solution negative 2/3 and negative 1/4. And these are our solutions. Okay. Now, there's one other category that I want to talk about. My plan is to probably revisit this technique tomorrow as well as some warm-up questions. I think it's probably the most challenging technique of solving quadratics you guys will deal with, because after this we'll have the square root property and the quadratic formula, and while they might be tedious, I think they're straightforward. You don't have to do that much independent thinking like these questions. These questions are a little tricky because these examples were pretty straightforward because all the terms were positive. But when we introduce negative terms, they get a little more complicated, because then you have to play with the signs in order to make them correctly add. And we'll have some of those later. So there's another technique that I want to talk about. Let's see, what is this called? It's called the perfect square. Where did I put that? Okay. So writing quadratic equations as differences of squares. So do you guys remember the difference of squares formula that we did when we were rationalizing denominators for fractions that had radicals in them? If a squared minus b squared, I'm sorry, not if, a squared minus b squared is equal to a minus b times a plus b. And this looks an awful lot like the factorization we are doing currently. So the general premise is if b is 0 in a quadratic equation, so maybe I need to change these letters because I think since we're using so many a's and b's, it's going to get confusing. The formula applies for anything that we do. So let's do x and y. This is x minus y and x plus y. So I'm going to add ample detail to make sure that we're clear. In this equation, if b is equal to 0, we can use this difference of squares formula. So as an example, in this equation right here, notice there is no x term. There's x squared, but x does not appear in this equation, meaning what is really happening is there's a 0x minus 9 here. So x, the linear x term with power 1, doesn't appear, meaning b is 0. That's the implication. We can use the difference of squares formula. So here is x and here is y squared. And I can factor this as x minus y, x plus y. So you're going to get really good at this because it saves you a lot of pain. But this is the same thing as x squared minus 3, x squared plus 3 is equal to 0. That's the factorization of this perfect difference of squares. And you can actually redistribute this and it'll make sense, and it should make sense in your mind. If I do 3 times negative 3, I will get negative 9 out. But then if I add negative 3 to 3, I get 0, which is why that middle term doesn't appear in the center. And this gives me solutions 3 and negative 3. Let's try this. Can I do anything with this equation? Is this a difference of squares? It's not a difference of squares. It's a sum of squares, and there is no formula for this to help us out. So you're out of luck. So remember, this is a difference of squares formula. So if your equation is not a difference, there's no way you can apply the difference of squares formula. Let's try another example. So what should this factor to using the difference of squares formula?
X minus 4, x plus 4. No.
Yep, exactly.
Oh.
Have some confidence, you were right.
I didn't know if you had to break it down to 2.
No, don't have to go that far.
Okay.
So right away, this is nice because 16 is a perfect square because 4 times 4 is 16. So we can very easily pick out what those solutions will be. It will separate as -4 and +4, and this will give me solutions -4 and 4. It gives me these double solutions. But let's try something a little different. This is probably something you don't need to know for your homework, but it's an interesting idea. So notice this is not a perfect square any longer. It is still a difference of two terms, but it's not a difference of perfect squares. But what I want to do is use this idea. The square root of 15 times the square root of 15 is 15. So root 15 squared is 15. So what I'm going to do is write this as x squared minus root 15 squared. And we're there. This is a difference of squares. It's just that this square involves a radical. This will give me x minus root 15 times x plus root 15. And it will give me the solution x is plus or minus root 15. So don't be afraid if you don't see a perfect square. You can, no matter what the number is, no matter what, you can always do this radical technique. So if this was x squared minus root 14, you could make that root 14 here, root 14 here, root 14 here, and you would get solutions out. So it works regardless of whether it's a perfect square. That's what I'm trying to illustrate with this example. Okay. So now what we're going to do is talk about the square root property of solving quadratic equations. So here's a rule for you. If x squared is equal to k, so I'll put rule here. That means x is equal to plus or minus root k. And this is actually a slightly more straightforward way of solving perfect square equations. So let's try up here. If x squared minus 15 is equal to 0, what we can do is set this equation up like this. If x squared minus 15 is 0, then x squared is equal to 15. Then we can apply the square root property. What I'm going to do is take the square root of this. And x will be plus or minus root 15. But does anyone know why I get plus or minus values without the context of this previous example that we did? So let's re-solve the question. Let's think about, is negative square root of 15 squared, right? Because that's supposedly a solution to this. Is this a true statement? What I'm thinking of is this. Right, I'm thinking of the original equation we had. And these are the two suggested solutions, plus or minus root 15. So hopefully when I re-substitute x in, it does give me a true statement, right? Hopefully it is. And this actually is true because notice this negative sign right here doesn't matter when I square a term. I still get positive 15 out. Same with positive root 15 squared. That definitely is equal to 15. So these are two different values that give me true statements. And whenever, so I'm going to add this. Whenever we take the square root of an unknown, we get plus or minus solutions. And don't forget that, because it will be essential as we solve these questions. So I'm going to add a blurb to the square root property as well. This can be used whenever b is 0, no matter what. And that is an insanely powerful technique, because if I have any equation, so we'll continue with some examples, and I'll leave that up there so you guys can write that if you are taking notes. But if I have this question right here, notice there is no x term. There's only x squared term. So b is equal to 0. So I can use the square root property. What I need to do, though, is isolate the term x squared. So I'm going to subtract 1 over to get 6 on the right-hand side. And then I can divide by 4 here. I don't actually have to, but it makes the algebra a little more easy. So I have x squared is equal to 3/2. And then I can use the square root property. Take the square root. And my solution is this. What am I missing? I forgot something.
Plus minus sign.
Yep, plus or minus, because I took the square root of something that's unknown. X is an unknown. That's why we're trying to solve for it. So when I take the square root of x squared, I need to be careful and incorporate the plus or minus. Okay, so let's do a couple more examples of this, and then I'm going to add a slight alteration, and we'll see what happens when we change it up a bit. Let's try. So let's try and play a thought experiment with ourselves and say I didn't give you this question in the context of this section. Say I just said solve for x. What should your thought process be on how to solve this? Does anyone want to like shout out a rule that you're thinking about? What is your own thought process on the technique I'm using to solve for this? We have a couple techniques now, so now we need to develop some sense of which rule to use when. Anyone have an idea? So the easiest first idea is b equal to 0. Because if the answer is yes, use square root property. If the answer is no, then we need to try and factor. Then we need to ask ourselves, when we get to this part, is a equal to 1? Is a equal or not equal to 1? If a is equal to 1, actually, I need to write this tree in a slightly different way. So once we factor, then we say, is a equal to 1? Have you guys had these decision trees before? You might have done it in like some other class of developing some type of like rule chart that you can follow down. So if a is equal to 1, so yes, then we can factor normally. If a is not equal to 1, then factor by grouping. So here is our thought process. So let's look. Is b equal to 0? Any idea?
Yes.
Yes, b is equal to 0 because x, a regular x term doesn't appear in this equation. There's just an x squared term. So since since b is 0, let's just use the square root property. So that's me subtracting 6 over. That's me dividing 3 over. And this is me taking the square root of both sides. And you're done. That was really straightforward once we figured out what rule to use. The hardest part of these questions are what rule to use. So let's change it up a little bit. What if I have something like this? Anybody want to suggest, just so it can be a naive guess, what if I gave you this equation and I didn't tell you this technique we're about to do, how would you try and solve this?
Distribute the 3.
Yeah. So what I would maybe do is, so you maybe not quite distribute the 3, but start simplifying things. This is the same thing as x minus 4 times x minus 4 equal to 15. This is 3x squared minus 8x plus 16 is equal to 15. We can make our lives a little easier and get rid of that 3. So then this is x squared minus 8x plus 16 is equal to 5. This is x squared minus 8x plus 11 is equal to 0. But now you're stuck. Now we don't have a great way of solving this. And this is actually the wrong way. I'm actually going to still use the square root property. Use square root property. So I do want to emphasize, though, the reason why this doesn't work is we've hit a dead end right here. This is x equal to 0. And the only factors of 11 are 1 and 11. And there is no sum or difference of 1 and 11 that can get me to -8. So this, while albeit looks like it can be factored, actually can't be factored in normal ways that we have. It's unfactorable. But if we use the square root property, you'll see why these solutions are harder to find using factorization. What we're going to do is instead use the square root property. Let me get rid of that. So right away, I'm going to get rid of that 3 by dividing by 3 on both sides to get the quantity x minus 4 squared is equal to 5. But now right here, I'm going to take the square root. So now this second power and the square root will cancel to get x minus 4. And I get plus or minus root 5 over here. Remember, because I took the square root of something that's unknown that's squared, so I need to be careful and account for the plus or minus version of it. And now I can solve. This is going to be 4 plus or minus root 5. And these are our solutions. So let's add some contrast right now. We have this question right here. What I'm going to do is I'm going to write this in an easier way. And then say I have I don't need that parenthesis. So these are all versions of, well, they're not the same question. These are 3 different questions that look similar, but are very different in how we solve for it. So right here, I have a sum or difference of terms. Here I have inside, x is inside a power right here. Here I have something that can be written as x to a power equal to a number. And this right here, you need to factor. But we can't factor this, so it actually doesn't work out for us. But this is the form of a question that you would be required to factor. Here's something that we can use the square root property for. And here we can use the square root. So when you guys practice this, this is the kind of sense you need to develop, like what technique will get me to the correct answer. But if you look, this is still a perfect square. That's the big key right here. This is some perfect square if I simplify this out to like x squared is equal to 9. And it doesn't have to be an exact perfect square. This doesn't have to be 9. This could be like 7 or something. But at its heart, it's a perfect square. So I can take a square root of it. This is not a perfect square though. So I can't just take the square root of both sides and get a nice answer. I need to use some more advanced technique. But when I have a perfect square or a perfect square, I can always use the square root property. So I'm going to use another example to illustrate that. So since I have a perfect square here, I can take the square root. Right, the square root of 100 is 10, so it's plus or minus 10. So my solution is going to be 9 plus or minus 10, which is either 19 or negative 1. Those give me the same answer. So there's one minor technique that I think I'll probably discuss tomorrow, but it's called completing the square. So I'll add that and we'll do it tomorrow, I think. Tomorrow. Now what I want to do is talk about the quadratic formula. And this is either your best friend or your most hated formula. quadratic formula. So if I give you any quadratic equation, so any quadratic equation written in standard form, the solutions for x will always be this. So this is a big mess, but if you are looking for something that always works to solve quadratic equations, this always works. This always provides the correct solution. It's harder, but it's harder. So it can help you out if you're trying to reduce the total amount of techniques to remember to get you the correct equations. This will always give you the correct equations. It just might be really annoying to do. And the derivation, I don't feel is super necessary for you guys to know, so I'm not going to go through that process. I don't think it really illuminates anything interesting. But let's just try it out. Use the quadratic formula to solve the quadratic equation x squared plus 5x plus 1 is equal to 0. So notice this equation to solve for x, this is just a big formula involving all of the a, b, and c terms. So let's just pick out what those are. A is 1, b is 5, and c is 1. So let's plug everything in. X is going to be -5 plus or minus +5 squared minus 4 times 1 times 1. That's a times c. A and c are both 1, so it's 1 times 1. And be careful, everything here is in the numerator. So this entire expression is divided by 2a. A lot of students will just put the 2a under this term and not include it over here. But the entire numerator, this is a numerator up here. Everything is in the numerator over 2 times 1. So this isn't an acceptable form yet. We need to do some simplification. It's going to be -5 plus or minus 25 minus 4 times 1 times 1, which is just still 4 over 2. 5 plus or minus 21 over 2. And this right here is okay. This is a correct answer. If you really wanted to simplify it more, you could do this. -5 over 2 plus or minus √21 over 2. That's just me breaking this fraction into two different pieces, right? If a plus b over c, if that's a fraction, then this fraction simplifies to a over c plus b over c. So it always works, but it's tedious. But we also have some categories where maybe it doesn't work out so well, and I want to explain what happens. So what's a big restriction with this equation? What do you think are some possible issues that we could run into when solving for this expression right here? What are some restrictions that could occur? So if a is 0, for example, this formula won't work because we'd be dividing by 0. But that makes sense, because why would we be using a quadratic formula on something that doesn't have a quadratic term? This square term right here is quadratic. Also, if what's inside the square root is negative, we might have an issue. And we will discuss that. So let's solve this equation right here. So A is going to be 1, B is going to be 1, and C is going to be 2. So let's plug that in. Negative B plus or minus B squared minus 4AC all over 2 times A. That's me plugging in the numbers to the quadratic formula. Here I get minus 1 plus or minus 1 minus 8 over 2. And now I've run into a problem. I have a negative square root. And like we've discussed, a negative value under an even square root is an issue, because there's no 2 equal terms that I can multiply together in order to get -7, because for them to be equal, they have to have the same sign. But if they're the same sign, they will always be positive. So I've run into an issue. We have a way to deal with this. I'm not going to quiz you on this concept because it's kind of pointless, honestly. It shouldn't be in the curriculum, but for your homework, you will need to understand this. So this right here is called an imaginary solution. Now, don't get me started on the verbiage of imaginary. It has created generations and generations of math students who think math is fake if numbers are imaginary. It's just that imaginary is the opposite, or its conjugate to real numbers. And real numbers are just numbers that we know every day, like 1/2, 1/8, 2, 6. That's just the verbiage for those type of numbers. We call those numbers the real numbers, the real number line. So when we have something that exists outside the realms of real numbers, the I guess logical choice was to call them imaginary numbers. But the forefathers of math didn't intend to, or they didn't envision that calling it an imaginary number would make people skeptical of, math being legitimate. Because I remember dealing with a lot of students over the years when they said, "Oh, if mathematicians have to make up numbers, meaning they're imaginary, then math can't be real." But it's just a vocabulary issue. It is not an imaginary number. We actually have really profound math dealing with imaginary numbers. The way computers are made, you have to calculate things using imaginary numbers. So please don't become too skeptical. Don't become jaded about math. But I'm going to introduce this concept now, which is I, which stands for imaginary, is the square root of -1. This actually lets us solve this question now, because what I can do is rewrite this as -1 plus or minus -1 times 7 over 2. So this is -1 plus or minus √7 times -√1 over 2. And if I is the negative square root of 1, this is -1 plus or minus I √7 over 2. And this is how you would answer your questions on the homework. You're going to have some situations where the part is imaginary and you need to solve for it. So let's try one more. I need to add some like highlights around that. So if you guys go back to look in the notes, you can find it pretty easily. Let's try this equation. We're going to use the quadratic formula. So A is 9, B is 3, and C is 2. So let's get at it. X is negative B plus or minus the square root of B squared minus 4 times A times C all over 2 times A. So what do you guys think is going to happen inside the square root? Any suggestions?
There's gonna be a negative
Yeah,
number.
there's going to be a negative in there. So we can predict that we're going to get imaginary numbers based on just this term inside here, which is actually going to be really useful for us in a second. So negative 3 plus or minus the square root of 9 minus 72. So that's going to be 63, negative 63. So again, I'm going to peel off a negative and leave the 63 originally. And then I'm going to split up them as a product. You guys don't have to do this arduous part if you can see the next step. I'm just being abundantly clear now. And the square root of negative 1 is I. So this is negative 3 plus or minus I times the square root of 63 over 18. And there's probably some simplification I can do with this root 63, but we'll leave this as is for now. So if you notice though, I was actually able to predict the type of solution I got based on what was inside the square root. And that is actually a really, really powerful technique for us. And I'm going to give this as a section, the discriminant. The discriminant. Discriminant. It's A. So the discriminant is that expression that's inside the square root. And based on analysis of this expression for any general quadratic equation like this, right? So if I give you some quadratic equation, you can plug in B and A and C in here, and depending on what you get out, you can perfectly determine the type of solution you will get. And I'm going to write that down. So here's a little chart. So value of the discriminant. And then the result if you were to plug in this equation to the quadratic formula. What we're doing is we're analyzing the discriminant to determine what type of solutions I get out if I were to solve this equation using the quadratic formula. So if b squared minus 4ac, the discriminant, if it's exactly 0, what we get is 1 rational solution out from the quadratic formula. If this right here is greater than 0 and a perfect square, we get 2 rational solutions. Do you guys know what I mean by rational? You can just provide thumbs up or not. Rational meaning a fraction. And maybe I should be clear. It doesn't have to be an actual fraction like 1/3, 2/3, something like that. It could be 2. 2 is technically a very special rational solution. It's 2 over 1. It's still a fraction. So don't be confused. If you get a solution as like 6 and 8, this is something that this could fall into. This could still be 2 rational solutions. So if the discriminant is greater than 0, but not a perfect square, we get 2 irrational solutions. Irrational solutions meaning you're going to have like leftover square roots of like, 13 or something like that. So your solutions would look like this. Maybe x is equal to 2 plus or minus root 13 over 7, like that. These are 2 irrational solutions. This right here is an example of 2 rational solutions. The square root got knocked out because this was a perfect square. And when I take the square root of a perfect square, I get out just a number. If the discriminant is 0, we get x is 2 plus or minus 0. And that's why we get a singular rational solution. And then what's left for us? If the discriminant is less than 0, we get what we call complex solutions. Complex meaning imaginary solutions. So maybe x is 2 plus or minus I root 13 over 7, something like that. So what it looks like. Now, I don't have enough time to go into this as much as I want to. You might have some homework questions about it. So if you feel like you can't answer those yet, that's totally fine. This is why I make the due dates pretty fluid, because I don't want to be really restricted of like, I need to talk about all of these topics today. Like we can bleed, since we have longer lectures, we can bleed the time into the next lecture a little bit. But this is called discriminant analysis and will be really helpful for us to see into the future of what type of solutions we're going to get. So that is all. You guys can stick around if you have more questions or want to do more questions with me, but otherwise I will see you tomorrow.
I have a quick question.
Yeah.
So I started the worksheet for like the square root property,
Yeah.
and for like A,
Mhm.
I found the answer to be plus or minus the square root of 20.
Yeah.
Are we supposed to like simplify that further?
Yeah, I ideally I would like students to simplify it as much as I can. I feel like it is slightly unfair for me to do it though, because I haven't done a lot of examples like that. So, if you know how to, I'd say yes, but I'm probably not going to go around penalizing students if they don't simplify as much as they can.
Okay.
But yeah, it's good that you've noticed that, okay, the square root of 20 can be simplified quite a bit because there
Yeah.
is a perfect square somewhere in there.
Okay, sounds good.
Yep.
And then I was also wondering if you could walk me through um number 3 on the first page.
Number 3 on the first page. Identify the x and y intercepts of the equation above.
Yeah.
Sure. Okay, so let's first find the equation above.
Yeah, I found, well, I guess you could tell me if it's wrong. But I found the equation to be y equals 7 over 9x minus 38 over 9.
Okay. I believe that. I actually haven't done that
Oh,
algebra
okay.
yet in my mind yet, but I trust you to solve that. So using the slope you found above, find the equation of the line that passes through the points above. So that's the equation of the line that you found. So now let's find the x and y intercepts of the equation above. So find y intercepts. We're going to set the other variable equal to 0.
Okay.
So set x equal to 0. And to find x-intercepts, we're going to set y equal to 0.
Okay.
So whenever I'm trying to find an intercept of one variable, the first step is to set the other one equal to 0.
Okay.
Because if you were to try and think about this as like a graph, the x-intercept is where y equals 0. It's along the x-axis. Y is 0 along the x-axis. So solving for where the equation is equal to y equals 0 will give me the x-axis. Same with finding the y-intercept. The y-intercept will be where x is 0, and that will give me the value. So that's the kind of overarching concept, but honestly, it's just easier to do it in a lot of the cases. So let's find the y-intercept first.
Okay.
Finding the y-intercept, I'm just going to plug in 0 for x. (38 over 9). So,
Oh, so is it just y equal, or is it's just negative 38 over 9?
yep.
Okay. Okay.
So this right here, though, if you remember, this currently is an equation of a horizontal line. We need a ordered x and y value, which is going to be 0,
right.
comma, negative 38 over 9. This is a point now. This will give me a point like this right here.
Okay.
Same, so here's the y-intercept. And to find the x-intercept, I'm just going to set y equal to 0. So wherever y is, I'm going to plug in 0. This requires a little bit more algebra. What I'll do is I'll add 39. Oh, it's 38. I'll add 38 over 9 to the other side to get 38 over 9 is equal to 7x over 9. And I can actually cancel these 9s because what I can do is multiply 9 over here, and then it would cancel with this 9 and this 9.
Okay.
So 38 is equal to 7x. Divide by 7 on both sides now.
Okay.
And x would be 38 over 7. But be careful. Remember, this right here, now the way it's written describes a vertical line.
So we need it to be 38 over 7, comma 0.
Yep. Great.
Okay. That makes sense. I always like second guess myself when there's kind of like ugly numbers.
Yeah. So the way I made these questions, I kind of just threw in some numbers that I hoped would work out, but maybe if they didn't work out, it's not. I wouldn't say numbers being ugly is an indication that you're doing it wrong in my class.
Okay.
Sometimes I will actually make it intentionally ugly just so you guys can develop a sense and trust in your own math.
Yeah. Okay. And then lastly, I just want to make sure that I'm doing this right too. For the standard form for this equation,
Mhm.
would it be 7x minus 9y equals 38?
Let's see here. 7x minus, yeah, yep. So if I were to, for example, multiply by 9 through this, I'd get 9y is equal to 7x minus 38 over 9. And then you can rearrange this in any way you see fit, but I would do this probably.
Okay.
Yeah, so you can bring x over here, or you can bring y over here and put 38 over 9 over there, whichever you
Oh, so you can do it in different ways.
yeah, whatever.
Okay. Okay, cool. All right. I think that's all I have. Thank you.
All right, yep, great. See you tomorrow.
See you tomorrow.